Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, welcome to Lesson 20. Again, 4 interesting transformations of functions. Okay, classwork opening exercise. Fill in the blanks of the table with the appropriate heading or descriptive information. So we have the graph of y equals f of x. Translate y equals f of x plus k. So if we add a constant to the end of that, what does that do to the function? That's what this is saying. So this here says when k is greater than 0, like 3, f of x plus 3, that we would translate up by the absolute value of k units. So when we add 3, we're moving the function up 3 units, for example. Now it says, what would we do to translate down by absolute value of k units? And that would occur when k is negative. So k less than 0. Okay, not equals, because if it was equal, then we just have f of x, nothing would change. So it's got to be greater than 0 to translate up and less than 0 to translate down. Okay, so now it's saying it doesn't give us the function, but it's saying when k is positive, we're going to translate right by the absolute value of k units, and when k is negative, well, this is going to say the opposite of this. So let's just put that in first. Translate by, translate the direction. How about translate left by absolute value of k units. And what would that function look like? Well, it would be y equals f of, and we want the transformation inside the parentheses, so it's going to be x minus k. So if k is positive, that shifts it right. Remember, inside parentheses, negative means opposite. So when k is positive, x minus 3 would be a shift right 3. If k was negative, like negative 4, it'd be minus a negative or plus. X plus 4 would shift it left 4 units. The absolute value of the negative 4, which is 4 units. Okay. Scale factor. Scale by scale factor k. Well, the equation would be y equals some constant times f of x. When k is greater than 1, it's going to be a vertical stretch by a factor of the absolute value of k. Vertical stretch by a factor of the absolute value of k. And that occurs, it's going to shrink when k is between 0 and 1. So if it's a fraction that's positive, but a fraction less than 1, then it's going to shrink by a factor of k. And when k is greater than 1, it's going to be a vertical stretch by a factor of k. And then vertical shrink by a factor of k and reflection over x-axis would make it a negative number. So now if we're between negative 1 and 0, this would be shrinking and reflecting. If k was less than negative 1, negative 2, negative 3, negative 4, that is going to be a vertical stretch. Vertical stretch by a factor of absolute value of k and reflection over x-axis. Okay, so vertical stretch by a factor of absolute value of k and a reflection over the x-axis. Okay, so now we're given the function y equals f of 1 over k to the x. And it says horizontal stretch by a factor of k, and that would occur if k was greater than 1. So if k is greater than 1, it's going to be a horizontal stretch by a factor of absolute value of k. If k is between 0 and 1, it's going to be a horizontal shrink by a factor of absolute value of k. Okay, and the rest is done. If k was between -1 and 0, it's a horizontal shrink by a factor of absolute value of k, and the reflection across the y-axis when it's negative. And then if we go bigger than -1 on the negative side, or smaller than -1, then the horizontal stretch by a factor of absolute value of k and a reflection over the y-axis. Okay, page 2 brings us to an exploratory challenge number 1. And it says a transformation of the absolute value function f of x equals the absolute value of x minus 3 is rewritten here as a piecewise function. Describe in words how to graph this piecewise function. So it says f of x equals negative x plus 3 when x is less than 3, or x minus 3 when x is greater than or equal to 3. Well, in order to graph that, you'd graph negative x plus 3 for any values x less than 3. So starting with, say, you'd start with 3 but put an open circle, right? Because it's not included. So if you plugged in 3, you'd get negative 3 plus 3, or 0. Okay, and then you would choose choose 2, and then negative 2 plus 3 is 1, and plot that point, and so on. So you would graph the linear equation negative x plus 3 over to x values of 3, and then to the right of x values of 3, you would graph the line x minus 3. Okay, so in words, you could say, first, I would graph the line y equals negative x plus 3 for x values less than 3, and then I would graph the line y equals x minus 3 for x values greater than or equal to 3. Exercise 1 and 2. So this is an exercise, so pause the video, see if you can do it, and then come back and see how you did. Okay, here we go. Describe how to graph the following piecewise function. Then graph y equals f of x below. Okay, so this function has 3 different pieces. So you would graph this linear equation with the y-intercept of -3 and the slope of -3 for all values less than or equal to -2. And then we would graph 0.5x plus 4, which is the line with a slope of 1/2 and a y-intercept of 4 for all values between -2 and 2. And then finally you would graph all the points that are greater than 2 for the function -2x plus 9. Alright, so I will do this in 3 different colors. So let's start with, I don't know, it doesn't really matter. Start with red, and I'll just put a little mark here so you know that's the color I'm using for this. So these are for values less than or equal to -2. So I will put -2 in this equation. -2 substituted would be -3 times -2, which is a positive 6, minus 3, which is 3. So at -2, we're up at 3. So I put a dot right there. It said equal to, so I'm including that point. Then I'm going to go to -3, because we're going less than. -3 plugged in here would be -3 times -3, which is 9. 9 minus 3 is 6. So -3 would be up to 6. And then if I chose another value, like -4, -4 times -3 is positive 12, minus 3 is 9, and that would be right here. So then I would draw a line to connect those, starting here and going to, actually let me undo that. I want to go the other direction and go beyond. So I'll start here and go this way. Okay, and then I just need to rotate a little bit I like accuracy. And then I will draw my arrow like so, and that is f of x equals negative 3x minus 3. So that is that line to this point here, and then going left and up forever. Okay, so now I'll change colors to green, and now I'm graphing this one. So I want to choose values from negative 2 to 2. So at negative 2, plugging this in, half of negative 2 is negative 1 plus 4 is 3. So it's at this point as well. It'd be an open circle because we're not including it, but it's included from the other side. And then if I chose a value like negative 1, half of negative 1 is negative 1/2, plus 4 is 3 1/2. So that's negative 1 up 3 1/2, which is here. And then I'll choose 0. Half of 0 is 0, plus 4 is 4, so 0, 4, it's the y-intercept, which is right there. And then 1 times a half is 1/2, plus 4 is 4 1/2, so over 1 up 4 1/2. And then plug in 2, half of 2 is 1, plus 4 is 5, so it's right here, but it doesn't include that, so that would be an open circle. Let me make that a little bit larger so you see it's open. So that would be an open circle there, not including it. And then I would draw a line segment from here to there. And then finally, the last piece of the piecewise function is when x values are equal to and greater than 2. So now let me just move this out of the way. Okay, that was neat. All right, so then I plug in 2. 2 times negative 2 is negative 4, plus 9 is 5. So now I am including that point right there. And then when I choose 3, 3 times negative 2 is negative 6, plus 9 is 3. So over 3 up 3 is right here. And then 4 times negative 2 is negative 8, plus 9 is 1. So over 4 up 1 is here. And then one more. 5 times negative 2 is negative 10, plus 9 is negative 1. So over 5 down 1. And that just keeps going down in that direction with a negative 2 slope. So then I choose my line segment. If you're doing this on paper, please use a ruler. And this is going to go like so. And then I switch back to my pen, draw an arrow. Now you should label every piece. So now I'm going to say y equals, or f of x equals, it doesn't matter, negative 2x plus 9. And the green portion was f of x equals 0.5x plus 4. So there is the graph of the piecewise function listed here. And I didn't mark, but I did this one in blue. So there we have it. Okay, so there's our graph. Okay, page 3 brings us to problem number 2. And it says, using the graph of f below, write a formula for f as a piecewise function. So I would say f of x equals, and we have 1, 2, 3, 4 pieces. So I'm going to make a fairly large bracket like so. And I would say, I'm going to work on each piece from left to right. So I brought in this line segment, and what I'm going to do is put it right at the end there, and then drag it up like so, and lay it right on top. So as you can see, when I do that, you can find the y-intercept. Okay, you could do that with a ruler as well, or you could just count. So I'm here, I went up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. So I'm off just a little bit, so I just need that down just a little smidgen more. There it is, like right there. Okay, so as you heard me say, up 1 over 2, that's rise over run, that's 1/2. So I would write 1/2 x, and the y-intercept is negative 1/2, so I'd say minus 1/2, okay? And then over here, I'd say for x values less than 3, negative 3. So the greater than or equal to we'll use on the ends. We don't know where we're going to put it, but let's leave the middle as the unequal portion. So let's use the equals here. So this would be for x less than or equal to negative 3. So negative 3 to negative infinity, this is going that way. Okay, so now let me switch to red for the next piece. So before I do anything, I'm going to take my segment and move it up to this end and then down to this end. As you can see, the slope is 0. I don't really need the line segment at this point because I can see where it crosses the y-axis without continuing my line. So this has a slope of 0, so it's 0x, and let me just do that for now, and then 0x, and then it's minus 2 for x's that are between. So for x is greater than negative 3, but less than 1. So 0x minus 2 you can have, or if you just put this, you could just have, let's make it negative 2 if x is between negative 3 and 1. We just have 0. Okay, next piece. So now I'm going to move my segment again to the endpoint right there and swing it up like so, and then drag it beyond the y-axis so I can see where it's going. And you could do this with a ruler or just count. So first thing I do is find out what the slope is. So it was down 1, left 1, down 1, left 1. So up 1 over 1, up 1 over 1. Either way you look at it, it's got a slope of 1. So that's just simply x. And the y-intercept is negative 1, 2, 3. So if that continued to cross the y-axis at negative 3, so it's x minus 3 for x that is between 1 and this point right here is 4. So x minus 3 from 1 to 4. And then finally the last piece I'll do in purple. I'll move my line segment like so, just to see where it's going to cross the y-axis and what its slope is. So if I put that there, my y-intercept is 5, and down 1 over 1, 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 a slope of negative 1. So it's negative x plus 5 for all x's greater than or equal to 4. And there is our piecewise function. Okay, one other thing I could say about this too, we could assume this to go on forever and ever, or we could look at it as, okay, it's going to stop right at that endpoint, that's where it's going to be. Okay, so if that's the case, we need to fix this. So it's x is less, it'd be x is less than, let me see if I can fix that. Move this over here and erase that equal sign so I don't hit anything else, and then move it back up. Okay, so we could also look at this as x less than negative 3, but greater than this point here, which is negative 7. So we could look at it also as that. So negative 7 to x, and then x less than negative 3. So it's a from negative 7 to negative 3. We could also do that. All right, and if we're going to do that at that end, we can do that at this end as well. And if we do that, then we need to rotate this. And we would put our starting point of 4. Let me change the color to purple. Our starting point of 4. Put the x in between, and the x is going to 6, and this is 7. And you could put the equal sign at the end like so. Okay, just by looking at this, we don't know where it's equal, if it's on one piece or the other piece, so I would just put the equal signs on the ends. Okay, exploratory challenge 2. The graph of f of x of a piecewise function f is shown. The domain of f is. So here they actually tell you that the domain is -5 to 5. It does not continue forever. And the range is -1 up to 3. Mark and identify 4 strategic points helpful in sketching the graph of y equals f of x. Okay, so now they're just asking you to plot the points that would be helpful in graphing these. So you want to know where each piece ends. So these two are strategic. We want to know our y-intercept. And if we know the other ends, those would be also useful. Okay, and they say mark 4, so I guess you could get away with not marking the y-intercept, because you can figure that out just by looking at it. And you do not need to extend these pieces like I did up here. You do not need to use a ruler or that red line I used, because you can always find the rate of, or you can always find the y-intercept by using the slope-intercept form of a line. So if this point is -5, comma, -1, and this point is -1, comma, 1, you can find the slope by taking y2 minus y1 over x2 minus x1, and then find the y-intercept by substituting in one of these points. So you could use point-slope formula. Okay, page 4 brings us to part B, and it says, sketch the graph of y equals 2 f of x and state the domain and range of the transformed function. How can you use part A to help sketch the graph of y equals 2 f of x? Well, I'm going to go back to the prior page, and here's f of x, and I've already copied it, as you can see, and I'm going to move it to the next page. And then I'm going to put it on this graph where it was on the last one. And it crossed at, let's see, it goes from -1, 2, 3, 4, 5, -1, -5, -1 to -1, 1. Oops, wrong way. All right, so it goes from -5, -1, which is here, to -1, 1. So this point's got to be brought down here, so I need to scale this, so just give me a moment. Okay, so this function started at -5, -1, and ended at 5, 3. So -5, -1 to 5, 3. -5, -1 to 5, 3. I shrunk it down so it's on the right points. And now we're going to use this to sketch 2 f of x. So really what you have to do here is, when you get to a point, it's at -5, -1, we want the y value to double. So -1 times 2 is -2. So that would be right here. Okay. And then if I choose this point, that's -1, 1. Well, that's got to be doubled to 2, so that would be here. And this point is 3, 1, and the y's got to be doubled to 2. 1 times 2 is 2. That would end up there. And then 5, 3. 3 doubled is 6, so 4, 5, 6. So this function would go like this. We would start at this point and go to here. Start at this point, go here, and start at this point and go up there. Okay, so let me just clean this up a little. Okay, so there is y equals 2 f of x, and the blue one is y equals f of x. So we just used the graph and doubled all of our y values. So this was 1/2, double of 1/2 is 1, and here it was 0, and double of 0 is still 0. That's why they intersect there. Part C, a horizontal scaling with scale factor of 1/2 of the graph of y equals f of x, that's the blue one, is a graph of y equals f of 2x. Sketch the graph of y equals f of 2x and state the domain and range. How can you use the points identified in part A to help sketch your y equals f of 2x? Okay, so I copied f of x down, so let me label that. Okay, so now what we're going to do is graph f of 2x. So it is saying that it is a horizontal scaling with a scale factor of 1/2 of the graph y equals f of x, and it's the graph y equals f of 2x. So this is going to stretch it out, or actually it's going to shrink it because it's 1/2. So we're going to choose points. Here, let me get back to my segment here. Choose points. And for instance, this is the point -5, -1. We're going to change the domain this time. And half of -5 is -2.5. So it's 1, 2, and 1/2. So it's going to go here. Let me put the dots first. I don't know the other endpoint until I calculate it. So let's just put dots. So it's going to go from -5 to -2.5, -1, which is right here. And then this point here is -1. Half of -1 is -1/2, so that's going to go here. And then this point is the point 1, 2, 3. Half of 3 is 1 and 1/2, which will go to here. And then this point here is 5. Half of 5 is 2.5. So 1, 2, and 1/2 up the same number, which is 3. Now we're going to get our segment and connect those points. So we're going to draw a line segment from here to here, and then from here to here, and then from here to there. And then label that in green, f of 2x. So think about this. If I plug in -5, or if I plug in -2.5, times 2 is -5. It brings us back to the original. So f of 2x, let me see, how could we say that? So what we can say is the domain goes from -2.5 to 2.5. That's our domain, that's our x values. The range stayed -1 to 3. For every point x, y in the graph of y equals f of x, there is a point x divided by 2, comma y on the graph of y equals f of 2x. The 4 strategic points can be used to determine the line segments in the graph of y equals f of 2x by graphing points with 1/2 the original x coordinate, which is what I did, and the original y. And those points that were used were -2.5, comma -1, -1/2, comma 1, 1.5, comma 1, and 2.5, comma 3. Okay, page 5 brings us to exercises 3 and 4. Number 3 says, how does the range of f in exploratory challenge 2 compare to the range of a transformed function g, where g of x equals k, some constant, times f of x, where k is greater than 1? So that's going to stretch it vertically. So what we could say is this. For every point x comma y in the graph of y equals f of x, there is a point x comma k times y in the graph of y equals k times f of x, where the number k times y is a multiple of each y value. That stretches it vertically. So for values of k greater than 1, y equals k times f of x is a vertical scaling that appears to stretch the graph of y equals f of x. The original range, -1 to 3 for y equals f of x, will become -1 times that constant to 3 times that constant for the function y equals k times f of x. Number 4. How does the domain of f in exploratory challenge 2 compare to the domain of a transformed function g, where g of x equals f of 1 over k times x, where k is between 0 and 1? Hint, how does the graph shrink when it is horizontally scaled by a factor of k? Okay, here we go. For every point xy in the graph of y equals f of x, there's a point k times x, comma y. See the difference? K times, or x, comma, k times y. Kx, comma, y. In the graph of y equals f of 1 over kx, for values of 0 to 1 for k, y equals f of 1 over k times x, is a horizontal scaling by a factor of k that appears to shrink the graph of y equals f of x. This means the original domain from -5 to 5, we're talking domain now, x values, so x between -5 and 5, for y equal to f of x will become -5 times that constant to 5 times that constant for the function y equals f of 1 over k times x. Page 6 brings us to the end of lesson 20. Go to your problem set.